Okay, so let me start by thanking the organizers for inviting me here. When I got the invitation, I was thinking, what should I talk about? But finally, I chosen that subject, which is not maybe the main subject of the workshop, but it deals with, let's say, not too big, so few to many body systems, dipolar forces, and also dynamics and excitations. And I will be talking about the small clouds of ultracold atoms in artificial gauge fields, excitations, dynamics, and detection of topological states. So why bother? I think everybody knows the interesting physics happens in strong magnetic fields, which is example of a gauge field. Integer quantum Hall effect, for instance, which everybody knows the classical effect. You put the two-dimensional conductor into a strong magnetic field, you put the voltage in this perpendicular direction, and you see the current going in the other direction, transverse conductivity, due to the, of course, circular motion of the carriers of the charge in the magnetic field. So Lorentz forces, if you wish. This has a quantum, very strong quantum signatures, which are known under the name integer quantum Hall effect, discovered by von Klitzing in the 80s, for which he has obtained the Nobel Prize. Not only that, this is so robust effect, observation of these plateaus in the in the resistance or in the conductivity of the two-dimensional electron gases at low temperatures, is that it serves nowadays as a standard of resistance. Now so this, I should say, quantum Hall effect, because these plateaus occur at the conductivity, which is written here, is a quantum unit times natural number. Okay, there are more effects in strong magnetic fields, which have not really been very well studied in the condensed matter physics, because it's difficult really to get this kind of strong fields and this kind of resolution. This is an example of the physics of a single particle in the lattice, where you have a magnetic flux per lattice plaquette, which is a rational number here, and you plot the energy, accessible energy for the particles. They form bands, because it's a periodic system if the flux is rational, and then these bands split in very nice way, forming a so-called Hofstadter butterfly as you change the flux. So for the flux 1/2 you have one band accessible, 1/3 you have 3, and so on. So when you go to higher, so to say, rational numbers with higher denominators, the thing becomes this beautiful fractal structure. Even more exotic are, of course, strongly correlated states in strong magnetic fields, of fractional quantum Hall effect, and the famous Lafniz states. Why artificial? Well, if we want to mimic effects of Lorentz force or even more exotic forces, then the problem is that we could use just strong magnetic fields with ions, which are charged, but atoms are unfortunately, but for that, for the ions, we would have used such a strong, imagine that for electrons we have problems to achieve strong magnetic field. For ions, which are so heavy, it would be even worse. So it would not be possible by the Department of Energy in any country to allow for such experiments, I guess. Now the atoms are neutron, so you have to do something artificial or synthetic. Okay. And now that's so I'm going to give you some review of how we were thinking about this problem since maybe 10 years, starting from ancient era and thinking about rotating small clouds, then to medieval epoch, in which we will start to try to understand how in this small system strongly correlated states appear, and it turns out it do not have to be states related to fractional quantum Hall effect, already at nucleation of the first vortex and any kind of, let's say, transitions from one state to a state of different symmetry. There are very interesting strongly correlated states in small clouds. Modern times deal with laser-induced, I don't know, many people are...
many friends, huh?
Yes. And so modern times deal with a better way of inducing laser gauge fields, artificial gauge fields using laser techniques. and I will talk a little about what we do in this area, and postmodernist deals with dynamics and detection. So let me start with the ancient era. People, when they were starting to think how to create, let's say, artificial magnetic field in the gases, the first thing was to thinking about simply rotation, and analogy with rotating bucket of liquid helium. So the people, oh Jesus, starting to be annoying. Sorry. So the way to rotate the Bose-Einstein condensate was to squeeze it a little by the lasers, and then making, it's really like mixing by the laser, okay? And the first experiments where the vortices were created in the Bose-Einstein condensate were done by Eric Cornell using somewhat different technique, but I will show you here the very seminal experiments by, I remind you, very seminal experiments by Jean Dalibard at the École Normale, where they really were rotating like with these squeeze lasers, the Bose-Einstein condensate, creating this kind of even lattice, or so-called abrikosov lattice of vortices. Still, already at that time, everybody was thinking to go in the ancient era to the fractional Hall effect regime, in which, roughly speaking, number of vortices created should be comparable with the number of atoms in the system. So that's not an easy task for just this kind of rotating of the with the lasers, but and especially with the huge clouds of atoms. So the people were started to think in that time to do it with the smaller samples, and the task was to really go to achieve these strongly correlated states like the famous Laughlin state for the filling 1/3 for the
Maciej, if you turn off your wireless, you
if I turn on my wireless,
contacting you.
That is correct. And I did it. So the Laughlin state is not the only state of fractional computer to have a Hall effect, which is interesting. You know, it has very funny excitations, which are neither fermions nor bosons, they are anyons. When you exchange two of them, they get a phase p/3 for the filling factor 1/3. There are even more exotic states, like for instance, such a Pfaffian state, which is believed to be a state for electrons at filling 5/2, which has not only fractional excitations, which are anyons, but they are non-abelian. So they have some internal structure. When you exchange two of them, they undergo a unitary transformation. So it's even more exotic. They are described by this wave function here. So people were very thinking that maybe we can do it with the cold atoms, and in fact this also leads to kind of effective field theories that we could study using ultracold atoms, which are famous Chern-Simons theories. So what we have, of course, there was a lot of papers already in the beginning of this century that dealt with the confined system of electrons in quantum dots, two-dimensional gas of electrons, few electrons, even not so many, and a lot of exact diagonalization studies. So in order to do something new, we atomic physicists, we started to study either bosons, which are not so studied before, because they are not so common in condensed matter, or different interactions, in this case dipolar interactions, which are also not so. And in fact, the work was first in dipolar. So if you have a rotating system, the Hamiltonian for particles in harmonic trap looks like that, kinetic term, harmonic confinement, dipole-dipole interactions. I assume dipoles perpendicular to my two-dimensional gas. And this is in the rotating frame, so I have this total angular momentum multiplied by the frequency of the rotation. Now this I can rewrite in this form, so I have effective magnetic field in the, I don't remember now, symmetric gauge, right? Orlando gauge. Symmetric gauge. Orlando gauge.
No, symmetric gauge.
Symmetric gauge. Anyway, in this gauge, okay? And this is important because I'm controlling this Hamiltonian. This is maybe a comment that I should do. In all these things, when we do synthetic gauge fields, we really synthesize potentials, and we have control over that. So this is not gauge invariance, which is given by the nature. We can measure in this kind of systems quantities which are gauge dependent, even though Hamiltonians, which we try to, so to say, construct, are gauge independent. So the spectrum, etc., of such Hamiltonian does not depend on the choice of gauge, but I can measure in this system because I know whether that I'm rotating with the frequency omega. So So rotation nucleus magnetic field, shallowing of the trap, and again by changing this omega from small values to how too close to the perpendicular trapping frequency, I can go from weakly to strongly correlated regime. And that was the idea. In experiment, we had in mind the following things, that if you think in the case of contact interaction, the gap, the expected gap in the big systems was too small to be observed in the experiment. So people were thinking, let's go A, to smaller systems, in which everything will be easier to observe. B, let's go to new interactions like deep power. Now, smaller systems, there were already at that time an experiment by Steve Chu and Nathan Gemelka, who were trying to rotate the small clouds in the lattice. When we started around 2005 by looking on the thermodynamic limit with dipolar gases and calculated gap by using perturbation theory, and the result was very optimistic. Except it was maybe not correct, but it was overestimated because we made numerical errors in this paper, which is actually quite well cited. We have to correct it few 6 days later. We come back to this calculation, including also spin orbit coupling. So more complex, not only normal magnetic field, but also synthetic spin orbit coupling. And then we realized that these results were overestimated. If you add a little of spin orbit, then indeed you can get quite big gaps in the thermodynamic limit. So it's not so bad. But already at that time, we started to compare our results with the exact diagonalization in small systems. And in small systems, the results here were giving smaller gap than there. So that was one of the things why we came back to the calculations of that, guided by the exact diagonalization calculations with dipolar systems. Also, in the beginning, our studies were mainly concentrated on understanding what kind of quantities you can measure and eventually discuss in the context of suite of cold atoms, so different kind of correlation functions, pair correlation functions, and things like that. Okay, so let me show you some typical results what you get in this exact diagonalization. So this will be the Hamiltonian which I have for the dipole-dipole interaction in the so-called lowest Landau level. So I really reduce everything I am in the strong magnetic field, and the whole Hamiltonian reduces to the number of atoms, angular momentum, which is multiplied by this difference between the rotation frequency and omega pairs. So rotation frequency has to be smaller than omega pairs because otherwise the centrifugal effect will make me unstable, and dipole-dipole interaction. And this I have to diagonalize. Okay? And the typical results of diagonalization look like that as a function of Z in the units of omega pair. Now, this is only for the dipole-dipole interactions. And if I add this LZ term, so this one, then I can stabilize. You see, this state will be the lowest energy state, and this is really analog of the Laughing state in a small sample of atoms. You see that this interaction, exact diagonalization gives me not only obviously one state, ground state in this case, but it gives me all the excitations and things like that, and gaps. So in this sense, it gives me also information about dynamics. Now, if you look, typical things that you can, so to say, calculate with exact diagonalization and perhaps measure are the correlation functions. In this case, this is a pair correlation function. I put one atom, you see where there is a black, anybody has another one? Because this one seems to be, or I am not able to do it. I am not able. So there is an atom here, and I ask what is the probability of finding the atoms in the other place, and this is a typical pair correlation function. If I start at low frequencies or low angular momentum, my system is essentially behaves like an ideal Fermi gas. So it is like a bulk or like a droplet of a Fermi liquid, if you wish. And now if I go to, this is for n particles. If I go to higher and higher angular momentum or higher and higher frequencies, the system with dipolar interaction undergoes this kind of changes in which there is a kind of bump in the middle, a kind of periodic structure on the edge, which is actually to going to develop edge states, and in particular in the final stage, chiral edge stage of the Laughlin state. And there are, however, new, so to say, effects in dipolar gases which are not known in the contact interactions, which are this kind of rather, it's not very interesting. You see this kind of changing. I change the angular momentum not so much, and I get this kind of very drastic changes from band here to a hole and so on. We have been able to explain some of these effects using a so-called composite Fermion theory of Jane many years ago.
Well,
and
why do you have a hole at the end? I don't understand. Your system is still rotationally invariant. Right?
Huh?
Why is this
this is pair correlation.
Oh, this pair correlation is fine.
Sorry, I said this is where I put one atom and I look where the other is. Sorry. Because density itself is boring. It's, as you say, it's rotationally symmetric. There is nothing in density. There can be a hole in the middle when you have one vortex, but then there is nothing. So it's very boring in a sense. The structures you see in higher correlations, in these calculations, which are accessible, of course. Okay? So let me show you the Laughlin state look like that, more or less. So it really looks like a liquid in the middle, and then this thing, which is there, this is the chiral edge state. So it's the edge state which really breaks the time reversal symmetry and goes in one direction. Okay, you can indeed look into spectra and look for Laughlin state and ask yourself what is the gap that it has, and then you have to do it for a fixed angular momentum. This is what happens in measure. So this is the value of the gap which you can measure. In these calculations, it usually for the dipolar interactions without any spin orbit couplings, it was not very high in comparison to Fermi energy of this for fermions. But as I said, a small addition of spin orbit to this system makes this gap more or less 6-8 times bigger in the units of the responding, well, in terms of Fermi energy. Okay, so well, you can study also excitations here, in particular the quasi-Hall excitations, and also look, even with this such small systems, you can try to characterize the properties of the edge states, which is one of the important things. Let me go to medieval epoch. In the medieval epoch, we started to think, okay, is it really so that in all this exact diagonalization, when I calculate things, the strongly correlated states appear only when I have high frequencies and when I'm in this close to this Laughlin state? And then we started to look at low rotation frequencies and see for the process of nucleation of the first vortex. And this was a joint paper with Jean Dalibard. I didn't say yet that, but the main person who was our, so to say, cicerone in the world of exact diagonalization was Núria Barberán from University of Barcelona. Dani Danino was her student. So what we were studying here, we were really asking what happens when I let's say, rotate the system and then slowly adiabatically increase the rotation frequency. So we were using exact diagonalization here to really study the dynamics. Now what happens that at some moment in the mean field theory, there is a phase, well, maybe one shouldn't call it phase transition, but this is a change of the state, that is the ground state of the system. The system from the, let's say, homogeneous nice condensate gets a vortex one vortex in the middle. Okay, and the mean, if you look at the mean density from exact diagonalization, this goes more like that. Here the symmetry, the rotational symmetry is broken. As you can see, this has a little elliptic shape because we really have to rotate this. We cannot rotate something which is rotationally symmetric, so we squeeze it a little and then rotate. This is in the system, of course, in which we are rotating with the condensate, and so it is a little ellipsoidal. Yes, and then in a sense you can see that something like vortices come from both sides for the average density. Okay, and then there is a vortex created, and if you look at the phases of the system, you see that indeed there was a phase slip of there was no phase here, and then there are phase slips that are entering, and finally you have really a single vortex in the middle. Now, the question was, On the level of mean field theory, you have a solution which is like a smooth condensate and solution like a condensate with the vortex. How does it happen in the fully quantum case? Well, to the same, you can look at the quantity which tells you what are the. You can calculate your single particle density matrix, and you can ask yourself what is the highest eigenvalue of the single particle density matrix. If the system is exactly condensed, then all the atoms have the same wave function. So the highest eigenvalue of the single particle density matrix should be 1. Everybody has the same wave function, okay? So if you look for low frequencies, okay, this red line is exactly occupation of this condensed mode. It's roughly speaking 1. The green line here is the second occupied mode. And as you go beyond the critical frequency where the first vortex is created, more or less these two modes still occupy more or less 95% of the whole population of your many-body system. But they change their role. The guy who was smooth condensate gets occupied by 10%, and the guy who has a hole in the middle, the one vortex solution, gets something like 85% or something like that. Okay, so it's still a good condensate here. Mean field theory works quite well, even for 9 or 12 particles, but of course the solution is completely different. So what happens on the criticality? In the exact quantum system, what happens, you see that at some moment the occupation of these two modes is equal. And this is not a Schrödinger cat state, but this is really a very strongly correlated state, in which is a, roughly speaking, maximally entangled state in which I can have 0 atoms in one mode, n atoms in the second, 2 and minus 2, 4 and minus 4, and so on. So it's a maximally entangled up to the even state, because this is of the big, follows from symmetry of our system. Yes?
Can I just have a simple question? From experimental point of view, what is omega? Is it some sort of...
So the frequency of rotation.
I know, but is it like, we don't know whether the system is in equilibrium with the stirrer, right? So this is what is imposed, or what is above?
This is imposed here, yes.
What is imposed?
Yes, we have a little squeezed trap, and we are imposing omega, and the units are the trapping.
Yes, but so we don't know that the atoms have actually absorbed the angular momentum just because, in fact, we know that they will not, I guess, at low omega, right?
With low omega, they will not.
Yes,
No.
and so you stir, and then...
In some moment when I increase it, I will have to go, the only response is to...
But then you stir for a long time, right?
Yes, in this case it's adiabatic. We were really doing it slowly and looking for the response, but these are really adiabatic curves, the curves that I'm showing.
But because this resonance is sort of dynamical resonance, right?
Yes, absolutely.
It's not the energetic one, yes. Okay, and then I know when you hit the dynamical resonance, then how much angular momentum you actually pump in can then depend on how long you stir, right? It's your weight.
So you see, talking about dynamical resonance is correct if you do the Gross-Pitayevsky, okay? And if we do exact dynamics with exact diagonalization. And then if we do it adiabatically, we simply go from ground state to the ground state in the way that that I show here. And in the middle here, we have this ground state with 0, n, 2, n minus 2, and then so on, okay? So of course the regime of parameters in which you have the strongly correlated quantum state goes to 0 and number of atoms goes to infinity. It becomes narrower and narrower. It goes not exponentially, it goes algebraically, but still it goes to 0. So in a big system you cannot see it, but with the small guys you can see very interesting things. And this kind of very general mechanism how the symmetry is broken actually in quantum system of finite size. Because of course in a big system there is also such a thing, except that it's very narrow regime of parameters to see, but it is also there. Okay? So if you look for instance at, I show you some at the mean density level, I told you that the vortices were going, the vortex, single vortex were so to say coming from both sides. It's not true of course if you do a single shot measurement, which is shown here. It comes from here or from there, like in the Schrödinger cat. Okay?
So much in your numerical calculation, you introduce a small asymmetries?
Yes.
Okay.
That's why I told you there is ellipsoidal. So we rotate really ellipse. Okay, modern times, the whole thing is done now with the lasers. The first maybe paper on that subject was by Gediminas Hevzeliunas with Patrick Koval, Julius Sidulzeckas, Andreas Klein, they proposed to do the following thing: 3-level atom. You have, of course, a dark state here. When your Rabi frequencies and phases of the lasers depend on the space, when you go around the space, your dark state changes and gets a Berry phase. And this Berry phase is nothing more but the artificial gauge field. This is a nice construction because it can be generalized to, if you wish, spin orbit couplings, or as I call it, non-abelian fields. So if you have, if you take an atom which has, say, this tripod structure, you will have 2 dark states here, because there are 3 complex Rabi frequencies, if you wish. These 2 dark states, when you go around again the space and your Rabi frequencies depend on the space, will get a generalized Berry phase, which is really a Berry SU2 operator, unitary operator, which coherently can exchange between 2 of them. And this is like spin orbit. And of course, the person who has really pushed it experimentally is Ian Spielman in the group of Bill Phillips and Trey Porto, where he was using very similar idea in the rubidium, this case with Raman transitions and the famous Bragg scattering tricks, if you wish, which are, however, very essentially the same as, or very similar to this proposed by Gediminas and others. Okay, and the first paper that they have published in PRL was actually, you may say, trivial, because they were able to create uniform light-induced vector potential, which of course does not lead to any magnetic field, because it's uniform. But pretty soon, they were able to synthesize with these methods vortices. Okay, these are kind of not very regular because of lattice, like in the case of Dalibar, but still they were able to, because they are somehow they imprint this this laser thing, and then they wait, and vortices dynamically are created. So, okay, so we have started to work on that more or less in the same, more or less 2 years ago. So this will be my modern times. And the main people now, the new person who came to the group was again Bruno Julia Diaz, who was postdoc and now is back in the University of Barcelona. Nuria Barberen again, Dani Danino, her student, Tobias Grasmai, PhD student, and this was still collaboration with the Coleman Martin and Günther and Jean Dalibar. So here the simplest way of creating this laser-induced gauge fields is just to shine a laser with spatial dependence of both intensity and phase on the, so just a focused Gaussian beam, it's enough, on the 2-level system, okay? And if you do that, you can get indeed, you put a strong Rabi frequency so that you have dress states in which atom is really located, and then you can eliminate the upper dress state adiabatically, assuming that there is a big energy difference between the two, and you get indeed exactly the Hamiltonian that you want, so the atoms in the effective potential, which is in this case is in symmetric gauge, okay, I guess. And this Hamiltonian is the Hamiltonian that we have just discussed, but this time this is non-interacting. Now, depending on what interactions atoms have, you will have interactions, okay. However, in reality, of course, this is just true in the limit in which the Rabi frequency of your coupling is infinite. In practical situations, you have a correction to this Hamiltonian, which comes from adiabatic elimination of the excited dress state, and which goes like 1 over Rabi frequency. And the effect of this exact diagonalization was the subject of this paper. Okay, so the ideal case is presented with this red line, and non-ideal but realizable with real lasers and real things is presented in the dotted line. On the axis you have W is the width of your Gaussian beam, K is wave number, and L here is plotted angular momentum. As you increase this is like changing magnetic field, more or less. When I increase this parameter, I go from, let's say, condensate without any vortices to the first vortex. This is for 4 particles, I guess. It's not written here, yes, it's 4 particles. So 1 vortex means angular momentum 4, 1 one angular momentum per atom. Then there is another state here, another phase if you wish, and then the Laughlin state. The second state is in fact the Laughlin state with the quasi-particle. So this one. Okay, this one is actually Laughlin state with additional quasi-particle on top of it. This is all these corrections can be calculated here. In fact, the Laughlin state, of course, at the end is also deformed, but we can even calculate it to some extent quasi-analytically how the deformation looks. If you look at the density and the pair correlation, they look like that for the four atoms. Density, again, we are a little squeezed in one direction in order to allow for, because of the laser actually, it induces this kind of asymmetry now. It is not induced by the trap, it is induced by the laser. And then pair correlation functions has this kind of properties like you see. For the ideal system is large Rabi frequencies, and this is not ideal. Okay, interesting thing that you can study here in this kind of systems is even for the small number of particles, you can ask yourself whether you can see some traces of topological order. So what is done here is we really pierce two holes in our system of 4 atoms, which is in the Laughlin state, and then we exchange these two guys, and we calculate the phase. And if they are sufficiently far in this thing, the exchange phase is really goes to what it should go, which is pi half. This is bosonic system, I forgot to say. I changed bosons and fermions here very frequently. In this case, this is not dipolar interaction, this is just contact interactions for bosons. The phase should be 1/2, and it really gets 1/2. Okay, and this is it was unexpected for many people who do exact diagonalization. That already with 4 particles, you can get some traces of the correct topological behavior for anions at this level. And for this deformed cloud, if I have this calculation is for the ideal Hamiltonian. So assuming this Rabi frequency of my laser is huge. But this anionic property is maintained even in the deformed cloud. Not so good, but they are not maybe having phase 1/2, but they are having phase like 0.4 or something like that. Okay, another set of things that you can do if you consider this kind of 2-level atoms in the light of the laser is that you can really include, just by playing with the lasers, you can include an artificial spin orbit coupling, and this may lead to new physics. But before I do that, let me just talk about 2-component bosons before I had 1-component bosons with the ground and excited state, but now I have 2 spins in a sense, or 2 spin components if you wish. Okay, so if I consider this kind of situation, then in the literature on fractional quantum Hall effect, there are 2 situations that have been studied with a lot of care. One is that I consider the fermions which are polarized, so sometimes people call them spinless because they are all in the same state. And then, as you know, depending on the filling factor for bosons, I start with the filling factor 1/2 because bosons have a symmetric wave function, so 1 over even function. And the Laughlin wave function has a prefactor which goes like that. Okay, but then there is a method of getting a more interesting, in a sense, states, which are called red-Rizai states, which are obtained in the following state. I divide the particles into k clusters and put each cluster into a Laughlin state, and then symmetrize everything. And this is called red-Rizai series. It has a property that maximally k particles can be at the same time in the same position. So if you think about the Laughlin state as a state which gives you for the contact pair interaction energy, it gives you 0 because the atoms cannot be in the same place. These guys cannot have, let's say, 3 atoms in the same place, so they are the ground states of the Hamiltonian with the 3-body interactions, and exactly. So if K is 2, these are the 0 energy states of 3-body interactions. If K is 3, or 4-body interactions, and so on and so on. They are interesting states because they are not only believed, they are proven to have excitations which are these non-abelian excitations, topological order, and very exotic properties. Similar exotic properties have a so-called non-abelian spin singlet states, which are different from this, because here my particles are spinless, they are all in the same internal state, but here I consider exactly the 2-component states. So this again have something which is an analog of the Laughlin state, which is called Halperin state, in which I let the same spins repulse each other with the prefactor like in the Laughlin state. The spins down also prefactor like in the Laughlin state. But then there is another prefactor which tells me that spin up and spin down also in a sense don't like to be in the same place, but with the lower power of the difference between their position. Okay? And this is a so-called 0 energy state of 2-body contact interaction, obviously, because no particles can be in the same place. It corresponds to a filling 2/3, and it's a singlet from the point of view of spin. It's the total spin singlet. Okay? And then you can do the same construction as is done here is done for this state, and then you get a state with, if you wish, with the 0 magnetization and spin, total spin equals 0 by exactly dividing particles into clusters, each cluster into Halperin state, and then symmetrizing and so on. This family of states have been proposed or discovered as variational ansatz by Eddie Ardon and Karl-Jan Schoutens. And then, again, the states have never been observed in the...
So each cluster, in this case, has up and down particles?
Yes. So the difference is here I have only one spin, or if you wish, one internal state. Here I have 2 internal states. And this is very analogous construction, but of course the second one is a little more complicated. And this is what we try to do with this our laser. So, well, I will skip this. I will maybe just tell you that it shows that with this laser methods we can indeed create a state which is not the Halperin state, which I told you had the filling 2/3. But one can create with the laser, it looks like the state, non-abelian singlet state with filling 4/3, which is already the first of the family, which is non-trivial in the sense of having non-abelian excitation. So this kind of laser-induced gauge fields is a really tool, we hope, with small systems to achieve some of these very exotic topological states. I think I will skip the thing about non-abelian spin-orbit couplings. They also lead to, again, interesting topological states within the small systems up to 12, 10 atoms. And I will go to the dynamics. So one of the ways of dynamics is used nowadays in quantum systems in two, or is viewed, I would say, in quantum many-body system or few-body system from 2 points of view. One is all this. First of all, dynamics cannot be simulated efficiently, and dynamics cannot be simulated very efficiently. There is really a big problem of making good simulators of dynamics. With this small, exactly solvable, exactly diagonalized system, of course, I can simulate dynamics, but I'm limited by the size. So one of the things is that dynamics is really a field for quantum simulators. This is what people say. There is a lot of discussions, as you know, about dynamics in the recent years from a point of view of thermalization, whether in a closed system we'll do some quenched or adiabatic perturbations, what happens after that, and things like that. There is a lot of discussion about going exactly through the critical points, Kibble-Jurek mechanism, things like that. But another aspect in which dynamics was discussed in the last years is exactly detection. Okay? So here, for instance, in this recent paper with Tobias Grass and Bruno Julia Diaz, what we propose is we take one of the states for our small sample of atoms in artificial normal magnetic field, and we pierce the hole in the system with a laser. Okay? Now, if you do it in the condensate, you see what happens in this movie. I mean, I pierce a hole, and I let the system. Of course, this is not the eigenstate of the system, so the system starts to evolve. Okay, the hole has not been pierced in the middle, somewhere off the axis. What happens is the hole vanishes and comes back. And this is nothing more but the many body or few body, if you wish, collapse and revival. So the phenomenon that's known from quantum optics, I don't know, everybody knows what's a collapse and revival or not? Okay, due to the fact that the energy levels are not really harmonic, if you form a, let's say, coherent state in any quantum system, after some moment it will dephase, so the phases between different components will become different because these differences between energies are different. This is a collapse. But since this is a discrete spectrum, this is exactly and strictly speaking, always the dynamics is a quasi-periodic process. After some time you will have a revival, which is essentially proportional to the typical difference between the discrete energy levels. So if you do this in the condensate, you see this collapsing revival. If you do it in the state which is quasi-particle state on top of the Laughlin, which is the state that appears in our exact diagonalization right before the appearance of the Laughlin state, you see also collapse and revival. There is a hole, then this hole is filled, and then it comes back. Okay? Now, if you do the same thing in the Laughlin, this is an incompressible fluid. This is what happens. Okay? Just nothing happens. Okay? I mean, nothing. It rotates. But the hole remains a hole, remains a hole. So it's obvious that here you have a method of distinguishing the quantum phase, if you wish, by looking at the dynamics.
Sorry, Maciej?
Yes.
When you say, maybe I missed something, when you say no interactions, is that because the exact Laplace state where the interaction energy is zero, or because there was no interaction between two-body interaction at all to start off?
No, the interactions are all in all the things there are. But there are no.
So
I have to look for that.
Interaction.
Well, no interactions because Laughlin state kills the interactions. This is what was meant. Sorry. These slides were they are prepared by Tobias, I must say, and some statements maybe are not. But it's correct. There are no interactions in Laughlin state. They are zero exactly because this is the property. Okay, so you can even somehow you can in this when I told you that when you go from condensate one vortex state Laughlin quasi-particle, this is this first, so to say, strongly correlated state before you reach the Laughlin. You can even quantitatively describe this collapse and revival processes by looking on the properties of the wave function. So it's a kind of nice method really to characterize. I give you last slide a paper which is another way but similar of detecting topological edge state by using very similar ideas. This is led by Nathan Goldman, and as you see the whole bunch of authors including Spielmann, Zoller, me, Fabrice Gerbier, another one, a leader of this, Jean and André, no? Dauphin? I don't remember. So here, this is in print. In printing. So here the idea is the following. You have a topological insulator which has some edge state. It can be Laughlin, it can be fractional Hall effect, Hall effect state, it can be topological insulator in terms of spin state. You make two big holes here, and then you take them out. And then what happens is the edge state will propagate here on the border of your box in which you have of your trap, if you wish. And if you look at this indeed in the dynamics, you see something like that. So you start with something that looks like that in the density, and then you start evolving, in the movie, and you see that these edge states really go around the thing. In this case, we have assumed that the bulk of the thing is dispersionless, so it doesn't spread, which then allows you to see these edge states very clearly. But there is also a method of doing this with the dispersion-full bulk, which spreads, but then you do some kind of echo and makes it back, and then you see the edge states again. And with this, I think, again, this is an example of dynamics which allows you to see topological order. And at the end, I just want to ask you to buy this book, which increase my